The formula of a compound gives us the simple ratio of elements that make up that compound by moles, but we can also analyze and figure out by mass what the percent composition of a compound is. So we can do this two different ways. This first way, there is an actual sample and you're analyzing it, maybe in a lab, and you analyze this sample and find that it has 1.507 grams of magnesium and 4.396 grams of chlorine. So let's look at magnesium. If you wanted to know what percent of this sample was made up of magnesium, the percent of magnesium in the sample by mass, you would take the mass of magnesium and divide it by the total mass of your sample, and then multiply that by 100%. So we need the total mass of the sample, and it looks like we have 5.903 grams of sample, since we found 1.507 grams magnesium and 4.396 grams of chlorine. We divide 1.507 grams by the 5.903 grams, get a fraction, convert it to a percent, and that becomes 25.53% of our sample being due to magnesium, mass-wise. And we could do the same thing with chlorine, using the mass of chlorine out of the total mass of the sample and expressing that as a percent. There's only two elements, so we could have just subtracted this from 100 to figure it out, but here is the calculation for chlorine as well. If you don't have an actual sample, but you know the chemical formula of something, you can figure out what percent each of these elements is by mass in this formula using the molar masses. So by molar ratios, we could tell that there's 2 chlorine for every magnesium. So on a molar level, 2/3 of this compound is chlorine and 1/3 is magnesium, 67% and 33%. But by mass, it's not going to be as simple a ratio because these two elements have different masses. In order to figure out the molar mass of the compound, magnesium chloride, we really do most of the work that's required for this problem. We take 1 magnesium, 2 chlorine, add them all up, and we get the total molar mass. So for the percent composition, we just have to figure out of this total what percent is magnesium and what percent is chlorine. And we already have those numbers right here. So for magnesium, taking the mass that's due to magnesium over the total mass, and then expressing that fraction as a percent, we get 25.53% of the mass coming from magnesium. And then doing a similar calculation for chlorine, we come up with 74.47% chlorine. So it looks like this is the same sample that we had in the previous problem because these are the same percents. All right, let's just try one more example on this video, and then there are a few more in the note packet, but I think you'll get the point after just 2, and you can look up the other answers in the answer key. All right, so we're trying sodium carbonate. To get the total molar mass of sodium carbonate, we need to add up 2 sodium, 1 carbon, and 3 oxygen. And these are the results over here. The total mass is 105.99 AMU for the compound. What percentage of that is sodium? Well, we take the mass that's due to sodium, here in green, 45.98 AMU. We put it as a fraction over the 105.99 and then express the result as a percent. And this compound is 43.38% sodium by mass. So doing the same thing for carbon, the 12.01 AMU due to carbon over the total represents 11.33% of the mass. And then doing the same thing for oxygen, 48 AMUs for oxygen over the 105.99 AMU for the compound represents 45.29%. So these happen to add up to 100.00%. Sometimes due to rounding, you might get a little bit of a difference in this last digit. As long as you get close to 100%, that's a good double check. If it's 99.99%, that's okay. If it's 100.01%, that's okay. If you're only at a total of 87% or at 129%, you need to recheck your numbers. Let's take a look at the difference between an empirical formula and a molecular formula. So the empirical formula is the simplest whole number ratio of elements in the compound. It's the simplest ratio. And the way we provide a formula for an ionic compound, since an ionic compound is not hooked together in molecules, the formula is the empirical formula. So I had a video on this More Videos for Chapter 6 page. Maybe I'll post another copy, but if you want to look at this in Module 4, there's a video here, and it shows the structure of an ionic compound versus the structure of a covalent molecule. So we have sodium chloride here. It's not that there's a bunch of units of one sodium and one chloride floating around, one sodium attached to one chloride. There's this whole big cube of sodium and chloride, sodium ions and chloride ions stuck together, and the ratio is 1:1. That's why we write the formula as NaCl, not Na2Cl or NaCl2 or Na3Cl3. We just write the simplest ratio, and that's how we come up with the formula. But there's really a lot more than one sodium and a lot more than one chloride stuck together there. In contrast, let's look at a covalent molecule, our friend hydrogen peroxide, H2O2. So we are using the formula H2O2 not because it's the simplest ratio. It's actually not the simplest ratio. It's because each molecule of hydrogen peroxide actually has 2 hydrogen and 2 oxygen. So we are listing what is found in the molecule. The simplest ratio of hydrogen peroxide is really a 1:1 ratio of hydrogen and oxygen. So this would be the molecule, and then the empirical formula, the simplest ratio, let's put it in a different color. The empirical formula would actually be HO, because there's one H for every one O. But the molecule itself doesn't have just one H and one O. It has 2 H's and 2 O's. So when we write the molecular formula, which is what we usually write for hydrogen peroxide, it has H2O2. Okay, so here I managed to draw the Lewis structure of glucose over here. This is a molecule of glucose. We draw the formula as the molecular formula needs to represent the total number of carbons, hydrogens, and oxygens that are in the actual glucose molecule. So the molecular formula needs to be what's actually in the molecule, and then the empirical formula needs to be the simplest ratio. So the molecular formula, we'll put it over here. The molecule actually has 6 carbons, 12 hydrogens, and 6 oxygens. So that is a molecule of glucose. That's the molecular formula. So it's kind of like simplifying a fraction. If you had 6/12 as a fraction, you would simplify it by dividing both of these by 6 and making it 1/2. So there's really a 1:2:1 ratio of carbon, hydrogen, and oxygen in this molecule. And we wouldn't really write the ones. It's understood to be 1 if you don't write them. So CH2O, a 1:2:1 ratio, is the simplest ratio. So it looks like it's carbon with a water molecule attached to it. That's a little bit of an interesting observation. A lot of sugars and starches have this kind of empirical formula. And when people first discovered that, they said, oh, it's like a hydrate, a water molecule attached to carbon. So they called these carbohydrates, hydrates of carbon, because a lot of them have this simplest ratio. But here is the empirical formula. So the previous problem, we were getting the mass percent composition from the empirical formula. What if we had a sample and we actually figured out the mass percent composition by analyzing the sample for each element? Can we go backwards? Can we figure out the empirical formula? And it turns out that we can. It's kind of an interesting process. We have these steps here. First, you have to pretend that you have 100 grams. So even if the sample you analyzed is only 3.27 grams or 0.985 grams, pretend that you had 100 grams, because that's an easy way of converting the percents into grams. And then you convert the grams into moles for each element, because the empirical formula is a molar ratio. So you need to know the ratio of moles for each element. Then the 3 and 4, I mean, you're pretty much done after step 2, but 3 and 4 are getting this ratio to be in small, simple whole numbers, which is what we need for the empirical formula. Okay, so the first step here, we have our percent composition by mass. So these percents are by mass. We're going to convert these into moles and get the molar ratio. So step 1, we're pretending we have 100 grams. If we have 100 grams, then 55.01% of that would be 55.01 grams. So if we had 100 grams of sample, then 55.01 grams of that would be oxygen, 24.09 grams of that would be nitrogen, and 20.90 grams would be magnesium. So just pretending that we have 100 grams lets us work with grams instead of percents. Now we're going to convert these to moles for step 2. Okay, so we converted each of these to moles. We have to use different molar masses for the different elements, and we come up with a 3.438 to 1.719 to 0.8597 molar ratio. So this is the molar ratio. The only problem is that we can't write a chemical formula that looks like this. Even though this is the molar ratio of elements, I mean, chemistry is complicated enough with just regular small whole numbers here in chemical formulas. So we can't be writing chemical formulas like this. We have to get these numbers, this ratio, to be small whole numbers so we can have a normal looking formula here. So we need to change these to whole numbers without changing the ratio to each other. So whatever we do to one thing, we have to do to all of them so we don't change the ratio. So if we decide to double the oxygen, we also have to double the nitrogen and the magnesium. So as long as we do the same thing to every number, we will keep the same ratio. And the first thing to do is to choose the smallest number, 0.8597, and divide everything by that. The reason why we do that is because that's an easy way to at least get one whole number. If we divide 0.8597 by 0.8597, at least one of our elements will have a nice, manageable whole number integer there. But we have to do it to all of them, otherwise we're going to change the ratio. Alright, and luckily when we do this to the other two elements, oxygen and nitrogen, we come out with whole numbers for those as well. I'm going to write the metal first because that's how we usually write compound formulas. So 1 magnesium for every 2 nitrogens for every 4 oxygens in this compound. So it's probably the formula for magnesium nitrite. Just looking at that, that's what it looks like. But this is as far as we have to go here. The empirical formula of this compound. I want to do one where you don't get whole numbers after the step 3. I want to get one where we have to do step 4 as well. So here are the first 2 steps here, pretending that we have 100 grams so that we can say 52.92 grams and 47.08 grams, and then using molar masses to convert to moles. Now we have the molar ratio, and the rest is just getting these to be nice whole numbers. So let's try that trick where we divide by the smaller number, doing that to both, of course. Okay, so I wrote a few extra digits here. The previous problem I just kind of right away rounded to whole numbers. So here it comes out to be 1.5007649. If it had come out to be something really close to 2, like this we can just round to 2. If it had become something really, really close to 1, then we could just round that to 1. But 1.5 is pretty much halfway in the middle. So if you have something that doesn't, isn't really obviously close to one integer or the next, don't round that to 2. This is not a 1 to 2 ratio. Let's keep working. Let's keep this as 1.5, and we can do something to get it to be a whole number. So we have a couple hints in step 4 up above, but basically this is a 1 to 1.5 ratio. For a half, you can double it. So we can multiply both of these by 2, which gives us 2 moles of aluminum and 3 moles of oxygen. So the compound that we have here is actually aluminum oxide, Al2O3. So if we had rounded this to 2 and said it was a 2 to 1 ratio, that would not be completely correct. We have to be a little bit more careful and sometimes do a step 4 to go to get whole numbers. I'll go ahead and leave this last example for you to try yourself and check the answer in the note packet. All right, let's take a closer look at the relationship between molecular and empirical formula. Remember that the empirical formula is the simplest ratio of elements in the molecular formula. So before we were looking at the molecular formula of glucose, and then to get to the empirical formula, we essentially divided everything by 6. 6 divided by 6 gave us 1, 12 divided by 6 gave us 2, and so on. So the molecular formula is a multiple of the empirical formula. CH2O multiplied by 6 would give us the formula for glucose, C6H12O6. So the way to figure out what this multiple is by mass, because the molecular formula of glucose will have 6 times the mass of the empirical formula. If we found the mass of the molecule of glucose and we divided it by the mass of the empirical formula, CH2O, we would end up with the number 6. So that's a way to find the multiple here. First, we're looking at how to get the molecular formula if you know the multiple, if you know that it's 5 times the empirical formula, and again it's a carbohydrate, CH2O. So CH2O, the empirical, multiplied by 5 would give us a molecular formula with 5 carbons, 10 hydrogens, and 5 oxygens. So that would be the molecule if it's 5 times as heavy as the formula for CH2O. So here is just a little practice getting the formula mass of the empirical formula. So we want to know what's the mass of CH2O so that we can figure out that the molecular formula is 5 times as big or 6 times as big. And if we add all of these, we come out with a formula mass of 30.03 AMUs for the whole formula of CH2O. Here in this next problem, we have an empirical formula and we need to know the molecular formula, or we're trying to figure out the molecular formula. So we need to know how many times bigger is the molecular formula. If we knew what multiple it was, we could take that multiple, increase all of these elements, and get the molecular formula. How do we figure out that multiple? That multiple is the mass of the molecular formula divided by the mass of the empirical formula. We did an analysis on the molecule and we know that the mass of the molecular formula is 168.19 AMU. That's the molecular mass. And the empirical mass we can figure out if we add up all the elements here, 3 carbons, 4 hydrogens, and 1 oxygen, we get 56.07 AMU. So let's put that here. And we can see that the molecular mass is about triple what the empirical mass is. So that multiple N is 3. If we multiply the formula by 3, if we triple it, we get C9H12O3. And you can double check that and make sure that it has a molecular mass of 168.19, and it should.